This is Mrs. Zappia with Lesson 6, using tree diagrams to represent a sample space and to calculate probabilities. Student outcomes for this lesson. Given a description of a chance experiment that can be thought of as being performed in 2 or more stages, students use tree diagrams to organize and represent the outcomes in the sample space. Students calculate the probabilities of compound events. Pause the video and copy the essential question. What are 2 uses for tree diagrams? Suppose a girl attends a preschool where the students are studying primary colors. To help teach calendar skills, the teacher has each student maintain a calendar in his or her cubby. For each of the 4 days that they are covering primary colors in class, students get to place a colored dot on their calendar: blue, yellow, or red. When the 4 days of the school week have passed, Monday through Thursday, what might the young girl's calendar look like? One outcome would be 4 blue dots if the students chose blue each day. But consider that the first day, Monday, could be blue, and the next day, Tuesday, could be yellow, and Wednesday could be blue, and Thursday could be red. Then this girl's calendar might look like this. Or maybe Monday and Tuesday could be yellow, Wednesday could be blue, and Thursday could be red. In that case, her calendar would look like this. Maybe Monday and Tuesday and Wednesday could be blue, and Thursday could be red, and so forth, so on and so forth. As hard to follow as this seems now, we have only mentioned 3 of the 81 possible outcomes in terms of the 4 days of colors. Listing the other 78 outcomes would take several pages. Rather than listing outcomes in the manner described above, particularly when the situation has multiple stages, such as the multiple days in this case, we often use a tree diagram to display all possible outcomes visually. Additionally, when the outcomes of each stage are the result of a chance experiment, tree diagrams are helpful for computing probabilities. Example 1. Imagine that a family decides to play a game each night. They all agree to use a tetrahedral die, that is to say, a 4-sided pyramidal die where each of the 4 possible outcomes is equally likely, each night to randomly determine if they will play a board game, B, or a card game, C. The tree diagram mapping the possible overall outcomes over 2 consecutive nights will be developed below. To make a tree diagram, first present all possibilities for the first stage, which in this case is Monday. When you're making a tree diagram, the first step is to create what the first stage is. The first stage in this case will be Monday. The second stage in this case will be Tuesday. And then the third column will be the outcomes for the games. So the first stage, Monday, the dice could land and they play a board game, or the dice could land and they play a card game. So the outcomes for Monday are either board game or card game. Then from each branch of the first stage, okay, so this is a branch in the first stage, and then from there we're going to go to Tuesday. So step 2 is from each branch of the first stage, attach all possibilities for the second stage, which is Tuesday. So on Tuesday, they could play a board game or a card game. Branching that off from Monday's outcome then would be board game, board game. So that outcome is BB. Or board game, card game, which would be BC. So here we're taking the possibilities for the second stage and branching them off each of Monday's stages or outcomes. Note, if the situation has more than 2 stages, this process would be repeated until all stages had been presented. What they mean by that is you could be playing games on Monday, Tuesday, Wednesday, Thursday, etc. So tree diagrams can be used for more events than just 2. Question A. If BB represents 2 straight nights of board games, what does CB represent? CB would represent cards on the first night and board games on the second night. CB would represent cards on the first night and a board game on the second night. And that is the outcome right here. Cards, then board game, and so the outcome is cards and board game. It's often helpful when you're making a tree diagram to think in terms of a dotted line connecting the second stage to the outcome for that stage. For example, cards, then board game, dot, 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 and that would be the outcome cards and board game. Cards, then cards, dot, 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 and the outcome is cards, cards. From the first stage, board game, then cards would be BC, and from the tree diagram at the top, Monday board game, Tuesday board game, dot, 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 and then the outcome for that is BB or board game, board game. Question B. List the outcomes where exactly one board game is played over 2 days. So let's take a look. Here we have board. That is not exactly one board game, so that does not qualify. The next outcome was BC, which is board game, card game, so that qualifies. Board game, card game. The next outcome is cards, then board game. Well, that's exactly one board game, so that counts. And then the last outcome is cards, cards. And that does not have exactly one board game, so that one does not qualify either. How many outcomes were there? There were 2. 2 outcomes. Example 2. In the example above, each night's outcome is the result of a chance experiment, rolling the tetrahedral die. Thus, there is a probability associated with each night's outcome. By multiplying the probabilities of the outcomes from each stage, we can obtain the probability for each branch of the tree. In this case, we can figure out the probability of each of the 4 outcomes. This is an important paragraph. Go back and highlight that. By multiplying the probabilities of the outcomes from each stage, we can obtain the probability for each branch of the tree. For this family, a card game will be played if the die lands showing a value of 1. So a value of 1 will be playing cards. And a board game will be played if the die lands showing a value of 2 or 3 or 4. 2 or 3 or 4. And then the family would be playing a board game. This makes the probability of a board game on a given night 0.75. The probability of a board game is 0.75. And make sure that you understand where that 0.75 comes from. Remember that landing on a 1, this would be a probability of 0.25 because there are 4 numbers on the dice and 1/4 is 0.25. Then there are 3 ways that you would not be getting or not be playing a card game. And so the probability of not 1 is 1 minus 0.25, which is 0.75. So not getting a 1 would be getting a 2, a 3, or a 4 and playing a board game. Okay, continuing. The probability for 2 of the 4 outcomes are shown. Now compute the probabilities for the 2 remaining outcomes. I've increased the size so that you can see that the paper has shown the probabilities here. The probability of a board game is 0.75. Then continuing on that branch, the probability of a board game is 0.75 and the probability of a card game is 0.25. Then the probability that you will be playing a board game and a board game is the probabilities multiplied together. So 0.75 times 0.75 is 0.5625. The probability of board game then card game. The probability of a board game is 0.75, the probability of a card game is 0.25, and the probability that you will be playing a board game then a card game is 0.1875. So here notice that the probability of playing a board game 2 nights in a row is 0.5625, about half, a little bit more than half, and the probability that you'll be playing a board game then a card game is lower, 0.1875. So back to question A. The probabilities for 2 of the 4 outcomes are shown. Now compute the probabilities for the 2 remaining outcomes. They've already written down the probabilities here for us, so we just need to calculate the answer. First, the probability of playing cards is 0.25, and then the probability of landing and choosing a board game is 0.75, and the probability that we'll be doing cards then a board game is the product of those two numbers. And we multiply that together and we get 0.1875. Notice that it's the same probability as playing a board game then a card game, just in the reverse order. Finally, we have the probability of playing cards 2 nights in a row. The probability for cards the first night is 0.25. The probability for cards the second night is also 0.25. And so we multiply those probabilities together. 0.25 times 0.25. And that gives us a product of 0.0625. That's a pretty low probability. All right, check, we've done that. Question C, what is the probability that there will be exactly 1 night of board games over the 2 nights? So our outcomes were these. We had BB, BC, CB, and CC. What is the probability that there will be exactly 1 night of board games? All right, so this one does not qualify because it has 2 nights of board games. This one qualifies, and this one does not qualify because there are no board games. So we can have either BC or CB. The probability that one of them happens is the sum of the individual probabilities. Let's write that down. And this is from a previous lesson. The probability of BC or CB is the sum of the probability of BC added to the probability of CB. The probability of BC, we have that from our previous problem, and that was 0.1875. The probability of cards then a board game is also 0.1875. The probability that we'll be doing one or the other, and the answer is 0.375. And that is the probability that there will be exactly 1 night of board games. Notice these are called disjoint events. And this is just a vocabulary word to be familiar with. Disjoint events are 2 events that cannot happen at once. Disjoint events are 2 events that cannot happen at once. That's a disjoint event. The exercises two children problem. Two friends meet at a grocery store and remark that a neighboring family just welcomed their second child. It turns out that both children in this family are girls, and they are not twins. One of the friends is curious about what the chances are of having two girls in a family's first two births. Suppose that for each birth the probability of a boy birth is 1/2, or 0.5, and the probability of a girl birth is also 0.5, or 1/2. And that's because when you have a baby, it can have a gender of boy or girl. There are two outcomes and they're equally likely. Number 1, draw a tree diagram demonstrating the 4 possible birth outcomes for a family with 2 children. No twins. Use the symbol B for the outcome of boy and G for the outcome of girl. Consider the first birth to be the first stage. Refer to example 1 if you need help getting started. Pause the video and attempt to make your tree diagram. Remember that your first step is to write out the stages. The first stage would be the first birth. Then what would the second stage be? And then you'll want to list your outcomes. Pause the video and complete this exercise. All right, let's see what you have. The first stage is the first child. The second stage is the second child. And the third column will be your outcomes. When you're making a tree diagram, you want to spread out your data because it's going to branch out. So our first child could be a boy or a girl. So I'm going to move down a little bit and put B for boy and G for girl. Notice how I've spaced them out, leaving a little room above and below each letter. Then your second child can also be a boy or a girl, and that branches out from your first stage. So here we have boy, and the second one could also be a boy, or you could have a boy for the first child and then a girl for your second child. Then those outcomes would be boy, boy, and this outcome would be boy, girl. And that's if your first child is a boy. If your first child is a girl, then your second child could be a boy or it could be a girl. So your outcomes when you have a girl first are girl, boy, or girl, girl. And these are the 4 possible birth outcomes. Part 2. Write in the probabilities of each stage's outcome to the tree diagram you developed above. Then, determine the probability of each of the 4 possible birth outcomes for the 2 children. Okay, so the next thing that we're going to do is we're going to write in the probabilities. And the probabilities we were told were 1/2, or 0.5. So we have 0.5 for every one of them. So just go ahead and write 0.5 by each stage and each outcome. Now it said to calculate the probabilities for each of the outcomes. So the probability for getting a boy and a boy is the probability of getting a boy, which is 0.5, times the probability of getting a boy, which is 0.5. 0.5 times 0.5 is 0.25. The probability of getting boy, boy is 0.25, or 1/4. The probability for boy, girl. The probability for each of those is 0.5, so 0.5 times 0.5 is 0.25. The probability for getting boy, girl is 0.25, or 1/4. Next, again, the probability for each is 0.5 and 0.5. And we multiply that and we get 0.25 again, and we will get the same outcome for the last. Let's go ahead and fix that. Small eraser, there we go. So that's 0.5 times 0.5, which is 0.25. All right, so we wrote in the probabilities and we determined the probabilities for each of the 4 possible birth outcomes. Part 3. What is the probability of a family having 2 girls in this situation? Okay, the probability of girl, girl. So the outcome is listed right here, and the probability is 0.25. And let's write that out with a sentence here. We'll say the probability of girl is 0.25. Is this greater than or less than the probability of having exactly one girl? Okay, so is this greater or less than exactly one girl? Well, exactly one girl. We wouldn't count boy, boy, but we can count boy, girl, or girl, boy. So boy, girl, or girl, boy. Do you remember how to find that out? The probability of either this outcome or this outcome is the sum of the individual probabilities. So the probability of boy, girl is 0.25. The probability of girl, boy is 0.25. The probability that they will have exactly one birth is the sum of those two numbers. And we add that together and we get 0.5. And that is the probability, go ahead and label that, the probability of exactly one girl. So the question is asking, are you more likely to have girl, girl, or one girl? So we're comparing 0.25 to 0.5, and 0.25 is less than. 1/4 is less than 1/2. So the probability of girl, girl is less than the probability of exactly one girl. In this lesson, you have learned tree diagrams can be used to organize outcomes in the sample space for chance experiments that can be thought of as performed in multiple stages. Tree diagrams are also useful for computing probabilities of events with more than one outcome.